Hello floodies and globe defenders, it's Critical Thing from Down Under. In this video I'm going to go through the analysis of that experiment and detail how we came up with the result that 98% of the variation of weight versus latitude can be explained by the WGS-84 rotating globe model. Before I get too far into the workings of the analysis, I'd just like to clear up one thing from the previous video. And I showed this diagram and I pointed these forces here, the gravity and the centrifugal force at the equator. And then I've marked this here, this centrifugal force at this latitude. Now, the way I said it, it was misleading. It's not incorrect. The way I said it, it could have been interpreted that I said the centrifugal force was operating along the radius, and that's not what I meant, so I just have to clear that up. So if we add to that diagram, the centrifugal force, of course, always acts in the outward from the spin, and the spin is along that B axis there, or the semi-minor axis. And in this case, the magnitude of the centrifugal force in that direction is 0.0294, or an acceleration of 0.0294 meters per second squared. Now the arrow that I've drawn there is the component of this force that acts upon the scales to affect the weight. So that's the only component that I was interested in, and that's I've correctly calculated that component as 0.0255, but I didn't explain that it was just a component of this main vector, which is perpendicular to the axis of rotation. So I'm sorry for not making that clear, and I hope this clears that up. This video is long because it has to be to explain what is a fairly complex process. It's important to reveal the methods used to process the data so that people can understand it and fairly criticize it. If you're not interested in the process, then you're not interested in the science of how I arrived at my result. Okay, let's have another look at the data, and I'll talk through how I process this data. Now, in processing this data, we have two problems. Now, I'll discuss the first thing there, which is that the actual weight does vary with height. The radius of the Earth is in some of the calculations, and so the gravity varies with radius, and so does the centrifugal force. So some of these readings were taken at different heights. So in this relationship of weight versus latitude, there is also another independent variable, which is the height. Now, I didn't want to have to deal with two independent variables. It would just mess things up a bit, and it would be very difficult to understand. So I wanted to translate it all into one independent variable, and that's latitude. So what do we do when we have readings which were at a different height? Now, what I did was I transformed them to the equivalent reading at my baseline height. And I did this according to each model. So whatever the model says that the reading should be at, say, 1,000 meters, I translated it down to my baseline height, and I normalized everything to the baseline, to 12 meters. So my model would say how much it should weigh at 1,000 meters height, for instance, and then my model would say how much it would weigh at 12 meters, and then I would apply that ratio to the actual measured weight and translate that from whatever height down to my baseline height. And this then gave me a baseline to compare all the readings with each other on an equivalent basis and just have the one independent variable, which was latitude. The other bigger problem is that the scales can be calibrated to whatever reading you like, really. So different people doing different measurements here, different scales. So not only do we have the problem of different scales, and they all should have been accurate to 0.01 of a gram, but we've got the problem that they were all calibrated at different places. So that's why you have calibration weights, so that wherever you are, you have a 500 gram mass, for instance, and then you weigh that on your scale, and your scale should read 500 grams. Now if it doesn't, you can adjust the calibration. So when you bring your scale to a different location, well, if you don't recalibrate it, it will measure different weight. And since everybody with their different measurements had a different calibration, and the model has its own calibration, so when I plot the model and what the weight should be according to the model, I have to make it calibrate to a certain place as well. So I have to find some way of rationalizing and normalizing all these different readings into what I would call as a normalized calibration. And briefly, that means that translating every weight according to the calibration ratio and aligning everybody's readings to the best fit to the model. Now this is done equally for all the different models, so they all have an equal chance of getting that advantage of a least squares fit to the curve. Now when in the process of doing this adjustment for the calibration, I maintained the relationship between the different samples. So this is the relationship of weight versus latitude. This relationship for each set of samples was kept intact so as not to skew the results. And I will go into the technical details of how that was done. So first I'm going to look at now the model again and how I worked out some of these formulae. Now I've put this is just for information only. I didn't use this radius up here. I except 6371000 in the rotating and non-rotating sphere model. That was the number used. These are the nominal forces of gravity with those when you use those radii. The G, constant G, the mass of the Earth, the product of GM is this number, which has been used in the calculations. The effective gravity at the equator. Now this figure includes the centrifugal force component, the gravity at the poles. This one includes no centrifugal force component because there is none at the poles. And you've got the semi-major, semi-minor axis. The first eccentricity squared, and the angular rotation, which is based on a sidereal day, and that's the official number for the angular
speed of the Earth in radians per second, and you can see that comes, it's very, very, very small, 0.0000729 radians per second. And there's another constant from the WGS84 model, m, and the flattening factor. Now, I've worked out this way of doing normalizing, first of all eliminating the height. My baseline for my model was that at latitude 30 degrees and a height of 12 meters above sea level, the weight will be 500 grams. So this is the calibration of my model. Now I had to align all the readings to that calibration. Now the first alignment is by height. So I did the working by hand in this spreadsheet, but I programmed it into a Python program that you will see shortly. So let's just say we made a measurement at 1000 meters. So if I have a sample that was taken 1000 meters in height and it weighed 500.08, at that height, my sample is the equivalent of 500.23. So how do we get this number here, this translated number? Well, we calculate for our model, we calculate this GH. Here we calculate it for the higher height and then my baseline height, and then we apply that ratio. So we multiply this 500.08, we multiply it by 9.79321023, and we divide it by 9.790160647. So we translate that to our baseline height using the model that we're currently using. This one here I have here is the WGS84 model, but the same process was applied for all models. So that's how I more or less eliminated that other independent variable of height. So this is to simplify things a bit. Now the height adjusted according to each model. I've changed the weight according to what the model says it should be. So that will make that reading equivalent, and we've really lost nothing in terms of predictions of the model. And if that relationship was wrong, then this reading here would come out as being wrong in the model too. So it's sort of the height is sort of included in my graphs, but it's so that I could graph it so that you could see easily what was happening. It's translated down to a height of 12 meters. Now we'll bring up the Python program. Now I've processed all the files that I had of data. I've put all my data into a file, processed all these files. I've programmed the constants into the program here and some formulas, and then I've worked out the various functions, some more formulas here in terms of functions, and then I've made each model I've assigned a particular class. So in this model in WGS84 I've given it a name. I've worked out I've given it a function in which we work out what is the effective force that is applied, and I've left this one open at a particular altitude, so we can feed any altitude into this, and that helps us with converting from one altitude to another and a lot of things. So what would be the effective force, which is the sum of the gravitational force and the centrifugal force? And then there's a centrifugal component which I calculate separately. So not always used, because this, in the WGS84 model for instance, the centrifugal force is already factored in there, but I will use it when I calculate for a non-rotating version of this model, but we'll get and see that. Then I'd have to calibrate this model to be the standard calibration, which something should weigh 500 grams at 30 degrees and 12 meters in height. And then the function for calculating the weight of something. Well, the weight of a 500 gram mass, I should say. These are all standardized to 500 gram mass. So the flat model, then there's a constant weight, constant force on it. In this case it'll be density or something, some such magnetism, or I don't know, whatever you flatties like to count as the flavour of the day. And the thing is, it's constant. A kilogram weighs a kilogram anywhere on Earth according to Pookie Pie. And then there's the calibration again, which means a 500 gram weight weighs 500 gram at 30 degrees latitude and 12 meters in height. Then we have the model non-rotating sphere. So there's no centrifugal component in this model, the same as there's no centrifugal component in a flat Earth, of course. And this is just, because it's non-rotating, it's just gravity, and it's a perfect sphere, and that will end up being constant too. And here's now another perfect sphere which is rotating. So we've got the effective force is the gravity, and take away the centrifugal force from that. You get the idea. A non-rotating spheroid, so we take the WGS 84 as the force, but the force is actually got to have the centrifugal force added to it, because in a rotating spheroid the centrifugal force makes it lighter, but if there was no centrifugal force we'd have to make it a little bit heavier. So we've used the WGS 84 model because the shape is the same but there's no rotation. Just for an exercise I've just put a straight line with a very small slope, and that's because of the R-squared analysis, and I want to show what happens with a straight line with a small slope on it. So this function here is for computing the sum of squares, the errors, and the sum of the squares of the error, and the sum of the squares, the total sum of the squares. So take the average differences, I've taken the differences, I've also kept the residuals here, which is for later analysis. So the residuals is the errors. Same thing. So here's how I do my height adjustment. I take the weight at the altitude that's comes from the data file. That's what this data point is here. The data point 0 is the latitude. The data point 2, which is the third item of data, is the height. So I've taken the weight according to the model at the measured height. I've taken the weight according to the model at 12 meters, and then I've adjusted my weight, which is data point 1, according to that ratio, W2 over W1. So I calibrate my scales to match up with the calibration of the model. Now this is the most complicated part, and is I take a first approximation, which is in general the ends up being a really good fit, but just in case it isn't, I have another step. So the sum of the squares calculates the differences, and it calculates the average offset, which is just not a sum of squares, which is just a sum. And I work out, well, are we too high or too low by these differences, the average offset. If we're too high, I just bring it down by that ratio that I may be too high, or too low, I bring it up by that ratio that we may be too low. So that just shifts every point in the series by the ratio that we might be too high or too low. So it maintains the relationship between the points, it just moves them up or down. So for instance, and it's a ratio because each weight needs to have the ratio applied. It should not be a linear just add or subtract. Each weight has to be treated exactly the same, otherwise it's not valid. So then I've just got this bit of code here about checking to see that that was a minimum by adjusting my weight by 0.01 of a gram either side, and just checking that we're at a minimum. And if we're not at a minimum, then I adjust the weight again. And I think you'll find that in all cases there's no need for further adjustment. So the first adjustment is the best one. So I have my analyzed data routine here. So which F is the model, so I call this for each model. I perform a calibration check, and so that should read at 12 meters and 30 degrees latitude, it should read 500. If it doesn't, well, then I've made a mistake. And then for each data point, I read the data points out of the file, make a list, and then I run the calibrate function on it, and then I calculate the sum of the squares of the errors and sum of the squares total, and I calculate the confidence. I've named that confidence, but that's really the correct term would be the percentage explanation of the model explains the observations, but we'll just leave that as named confidence now, and then I save everything. So here's my main loop. I've got all of my models. I run through all my models, process them all, and write the results to data files so that I can graph them. So before we do that, I just want to run one thing, because I've got in my first video I did on this weight change versus latitude, I took the average of my readings at a particular place, and then I plotted them on the graph. And I just wanted to run this. So there you go. I've run this this average for my data. I've taken all the points, all the data points, and averaged them for each location, and then I plugged them, and I've got a 99.9% match on the WGS84 model. The WGS84 model explains 99.9% of the variation, which was a bit fluky, I guess. The way I did it, I averaged all the readings at one location, and then I plotted those 4 points, and that ends up being only 4 points. So in one way it's valid, another way, well, some people may think it's a little bit dodgy, so I didn't count this in the final result. So the flat model explains 0% of the variation, and as I've explained before, the flat model predicts no change. But there is change, and the flat model will always explain 0% of something. And then rotating sphere 87.7, non-rotating spheroid 56.6. Anyway, these results are not used in the video. I'm just presenting them here for a little bit of information. So here's how the calibration works for the scales, however they're calibrated. This program attempts to then make all the calibrations equal. So this is the average offset you can see here, which is then after the adjustment of the samples, the average offset is 0. So you can see every model gets that adjustment. So it gets the calibration that best fits that particular model. Because, you know, the calibration, there's no way to tell different people on different parts of the world how they've calibrated their scales, really. I mean, when they calibrated them, it could have been a reading that's in a particular range, because of the scales are not entirely accurate. So I've just fitted everything as best I could to the particular model. So I've run all the models now. So go up to the top. Start at the top here. So this is my data. Compare against the WGS84 model. Do the calibration. Sum of the squares. The WGS model explains 97.6% of the variation. Wolfie's data. WGS model explains 95.9. Olivier, this is a little bit lower than I would like, but that's the result. The WGS model explains 67.9% of the variation. Mr. Thrive and Survive got an 83% score. That's not too bad. Greater Sapien, 98% score. And the total, I take all the readings by all these different people, and the WGS model explains 94%. Flat model explains 0. For my data, the flat model it's a 0 everywhere. That's expected. Then we get the rotating sphere model, and the numbers. Olivier gets a 99.9% out of the rotating sphere model, but he only had 3 samples, so the margin for error there is quite large. And when you make a conglomeration of all the samples, that's when your accuracy starts to go up. So in this case, rotating sphere, we ended up, you saw that in the summary, 90.1%. So this is how I got these results. And I've also produced now the residuals, which will also give a little bit of a picture of how confident we are that these numbers are right. And before we go to that, I've just got this linear model which has a very small slope on it. So the data varies by much more than the linear model predicts. So the linear model only explains 5% thereabouts of the variation. So that's just to compare with a flat Earth. This linear model says there will be a small amount of increase of weight versus latitude, and then that particular model generates a 5%. It explains 5% of the variation.
Okay, this video has gone on for quite a long time already. I'm sorry about that, but there were many things that I had to explain. Now, I also have many graphs to come which illustrate why the case for WGS84 is so compelling. I go into some of the sampling and statistics and why the data fits so well and why it doesn't fit so well for a flat Earth, and what that means exactly in terms of probabilities. I hope to see you then.